Awesome, thank you. So hopefully this will be for your fun and my profit. Maybe we have some profit sharing. We'll see how that goes. So thank you for the introduction. As was mentioned, my name is Pearson. I'm a penetration tester at Idaho National Laboratory. Just to say, I'm here as just an individual. This is personal research. Views and opinions expressed here are my own and not my employer's. Been working in InfoSec for about 6+ years. I also like playing board games, card games, Magic the Gathering. I spend too much of my money on that, so thus the need for profit. So we're going to be talking about Android applications today. You're probably mostly familiar with Android applications on your phone, maybe your tablet. But Android is also used in a lot of other embedded systems. So I just noticed we have an OWL video conferencing device here. This device under the hood, if you were to get into the firmware, is actually running some variant of Android. The Facebook's Oculus VR headsets run Android. The Amazon Alexa devices run a fork of Android as well. And I helped a family member set up a treadmill last year, and when we were booting it up and looking at the touch screen, the modern treadmill has all the modern Wi-Fi connectivity, built-in web browser, ability to watch TV. That device looked like it was running Android as well, based on the user interface. So a knowledge of Android apps and the Android ecosystem allows you to explore other devices besides just your phone or tablet. So start with a quick crash course on Android application design. An Android app is primarily coded in the programming languages of Java, or more recently Kotlin, which is a new language for Android that Google has been working on. An Android application is split into several different components. These components are generally somewhat independent from each other. We'll talk about a little more about that later. And each application is given a unique ID designator called a package. So if you're trying to acquire a particular Android app's files for analysis, you're going to want to know the Android package. We'll dive into that in a little bit as well. Android apps are compressed into a zip archive called an Android package. This is an APK file. This file is actually a zip archive. It had some other operations done to the files inside of it, so it's not quite as simple as just acquiring an APK and unzipping it, but it is more or less just an archive with the app's files. These files contain the code files that we need for doing reverse engineering. They also contain static resources such as image files. So if you have an application for your company and you want to include your company's logo, you can just embed it inside the app's files, and then that way your application does not have to download it from your website every time it's started up by your user. APK files are signed by a developer's certificate, and they're also signed by Google when the application is uploaded to Google Play. And Google uses this to try and control malware to a certain extent. If you have an application that is found to be malicious, Google can revoke the developer's certificate so that the application is no longer trusted by Android devices with Google Play installed, and that can help prevent the application from propagating. If we want to analyze an Android application, the first thing we have to do is we have to acquire the files so that we can analyze them for vulnerabilities. To do this on your Android phone, tablet, or whatever device you're using, you have to enable something called Android Debug Bridge, or ADB. ADB is also the name of a command line program that Google provides to interact with your device at a lower level. So those two terms are used interchangeably. In order to use Android Debug Bridge, you have to enable USB debugging. To do this, you go into your phone or device's settings, you find the build number, and you tap it rapidly 7 times. And as you're doing that, Android will pop up a little toast notification that says you're X steps away from becoming a developer. Once you tap it the 7th time, if you go back into the settings, you'll see a new option called Developer Options. We have a screenshot of that here. Go into Developer Options. First thing you'll have to do is actually turn them on. So just tapping on the build number in the settings doesn't actually enable it, just allows you to enable it. Once you enable it, you then want to turn on USB debugging, which is the second slider there in the screenshot. If you're planning to analyze applications from a Linux system, so I use Ubuntu on my laptop, there's an ADB package that you can install through your distribution's repositories. If you're planning to use Windows, you'll want to download the Android platform toolset from Google, and there's a link there at the bottom of the slides to download that. You may also need to install the ADB driver from Google. And once you do that, a quick disclaimer first, Google will give you a warning that says you're making your device less secure. If ADB is enabled and you plug your phone into a computer that you don't trust, there is the potential for malware on the computer to access some of the files on your phone. So you do want to be careful. Plug your phone into computers that you trust. By default, you'll have to approve a notification on your phone before the phone will allow the computer to pull data from it or talk to it at a deeper level over ADB, but that is something to be mindful of. You plug your phone into your computer and your computer gets malware. Now it's easier for somebody to siphon data off your phone. So that's just a little bit about Android Debug Bridge. Once you have that enabled, you need to find the package identifier for the application that you want to analyze. There's not really an easy way to get this. You can get it using Android Debug Bridge. It's a little bit involved. There's an easy trick you can do. You go to the Google Play Store and you look up the application that you want to analyze. You can look up in the URL, and there is a parameter called ID. And the value of the ID parameter is the application's package identifier. In this case, in this screenshot, this is for the Signal encrypted messaging application. And the identifier for Signal is org.thoughtcrime.secure.sms. So you just copy that value out of the browser, put it in a text file, and we'll use it here in a few steps to actually grab the application off the phone. So once you connect your phone to your computer, then you can use the ADB command and the package identifier we just got to get the application's APK files. So ADB syntax usually goes something like ADB followed by the commands that you want to run. And there's a lot of commands that ADB is capable of running. I'm just going to put the two here that we're going to use. So the second bullet point, ADB shell, PM stands for package manager, and then path. So shell says run this as a shell command on the Android device, your phone or tablet. PM's package manager invokes package manager that's in charge of installing and managing your applications. Path tells the package manager we want the APK file path for this particular package. So then you paste your package identifier, you run that command, and then third command, once we have the file path from the second command, we use ADB pull, which downloads files from your device and puts them on your local computer. Now we have a screenshot showing this in operation. So I run the ADB shell command looking for the APK path for the Signal application. And as you can see, the application path includes some base64 encoded values. I don't know if these are randomized, but they do change in between app installs. It's one of the reasons why we have to use the PM path to figure out where the APK file lives. We can't just predict where it's going to be. Then you pull it down. ADB will download it across your USB connection and will put it where you tell it to. In this case, I told it to put it in my current working directory. So you can see we now have a file called signal.apk. So now we can go ahead and start analyzing this file. And we are going to use a decompiler. There's a couple different options. You can use one called APK tool, or the one that I like to use, JADX, which stands for Java Archive Decompiler. And as a side note, JADX can be used to decompile other Java applications. So if you have a Java application like Atlassian's Jira ticketing tools written in Java, you can decompile some of the Java files from those applications and read them as well. But JADX can also decompile Android apps. So as we can see here, I run the JADX tool. I have a command line option, -- deobfuscation is what that stands for, deob. And then we provide the APK file that we want to decompile. It goes ahead and decompiles it. And then if we look in our current directory, now we have another subfolder. This one, in this case, is called Signal because I didn't tell it to name it anything different. By default, it will just name the folder with the same name as the APK file that you just decompiled. So that's pretty simple. It just takes a minute or so for it to run. And then we can start our analysis. So that folder that JADX created is going to have the code files that we're interested in looking at. In this case, they're decompiled, so they're plain text Java code that we can look at. And if you go into that Signal folder, or any folder for whatever application you're decompiling, you'll see there's two folders within that one. One of them is called resources, and one of them is called source. The resources folder contains resources such as images, like I mentioned earlier. If you have your corporate logo, it can contain any arbitrary files. So if you're a developer and you want to include a JSON file with text for whatever your app happens to use, you can put that in the resources folder. Other values such as strings. You can also have translations. So if you want your application to display text in English and Spanish and other languages, then you can put those in there as well. And then the source folder is going to contain the source code that we actually want to look at for vulnerabilities. The resources folder also contains an important file called Android manifest.xml. This file contains the definition, so to speak, of the application that the Android system is going to use to figure out what it needs to install, what your application does, does it have any background services that run, should your app be allowed to communicate over unencrypted network traffic. Those kind of questions are answered in the manifest. And we'll get into that a little more here in a bit. And by a bit, I mean the next slide. So it's an XML document, which you could probably tell from file extension, defines the application's internals, defines interactions, what applications can interact with different components. So our interest as a vulnerability researcher is this file will define externally reachable code, or a lot of the externally reachable code. Maybe not every piece of the app that could be interacted with from an external untrusted source, but it defines a lot of it. So that's where we're going to spend a lot of our time. So this is a screenshot showing you what manifest looks like when you open it up. This is, again, the Signal application. There's a lot defined in the manifest we're not going to cover. Most of what you see here are actually the permissions. So if an application wants to use your microphone, it has to define that in its manifest so that the Android operating system will then let it access the microphone or whatever else it happens to want. In this case, Signal needs access to a lot of things, so it has them defined here. You can also see the package identifier of the app in the manifest, but we already need to define that to get this far if that doesn't help us, but it's nice to see it listed there again. So we talked a little bit earlier about different Android components. So an Android app is split into different parts. One of the basic components of an Android app is something called an activity. And an activity is, in Android, you can just kind of think of it as a general purpose bucket for holding code. So an activity is where you can write Java code to do various arbitrary things. When you tap on your application's icon on your phone or tablet to launch it, what it's doing in the background is it's launching an activity that the application defined in the manifest as the main activity, or this is the activity that should be launched when the user tries to open my app. And then within that activity, you can have whatever code you want. So for most applications, you're going to have a loading screen. Maybe they'll have the logo of the application's developer or whatever else they want to do. But activities are not limited to just that purpose, but that's just an example. One of the other things about activities is they're somewhat independent from other activities. So you can have that one activity that launches when your application starts, when a user taps on the icon. You can also have an activity that launches, let's say you have a e-commerce application, Amazon.com or whatever, and you send out a push notification that says, sale, happening today. Well, if somebody taps that push notification, you want your app to open, but maybe it opens to a different activity. Depends on whatever purpose your app is serving, but our main point is that different activities serve different purposes. Inside the Android manifest, they are defined with an XML tag called activity, and within that tag, there is an attribute that we're looking for called Android exported, and if the value is set to true, then that means that other applications on your phone or tablet can start that activity. They can launch it and they can send data to it. So when we're looking for vulnerabilities in software, one of the general strategies you can look for is anywhere within the software that accepts external input. As an attacker, we can manipulate that input and try and get the application to do something it shouldn't. We can try to find something to exploit. So for an Android app, this is one of the common ways you can look for vulnerabilities. is activities where Android exported is set to true. That just means that we can interact with it. So going back to the manifest, this is an example application, activity within the Signal application. So I've highlighted it in orange, but there's an activity. We have the name of it, which will be important here in a second. But at the very end, you can see Android exported is set to true. So this is an application that another app on the phone can start, send data to, potentially interact with. So if we were looking for vulnerabilities in Signal, this application, or this activity might be one that we want to take a closer look at. So as we mentioned earlier, activities accept input. The input is supplied by the calling application, and external input should not be trusted. And if we want to figure out what the app is doing with the input, then we have to go look at the decompiled source code. In preparation for that, there's a couple points here about an activity lifecycle that we need to cover. So if you're programming an Android application and you're writing an activity, Android has some APIs and frameworks that your activity has to implement in order for Android to recognize it as such. If you're in Android Studio, it's essentially just a Java code file that has to implement certain methods. Some of the common ones are listed here. In order from left to right, the onCreate method is called when the activity is launched. So going back to our example where the user taps the icon, launches the application, that particular activity that gets started by Android calls the onCreate method, and that's where the operating system backs off and your application's code starts to run. So that method is really important. If we have an activity we can send data to, we want to look in that method and see what is the application doing there. Is it something we can exploit? The onResume method is called by the Android operating system when the activity is revisited. So if you have your mobile phone and you're using it, you're inside Signal texting, and then you leave Signal, you go to your browser, you're browsing the web. If you go back to the Signal application, what actually happened is Android paused Signal, put it in the background. Now that you've come back to it, Android calls onResume for that particular activity that was running. Trying to think of an example here. Let's say you're watching YouTube and then you go to your browser, so you leave the YouTube app, then you go back to YouTube. YouTube might want to do something like check, are you still on Wi-Fi? If you've set up YouTube to only play HD videos on Wi-Fi, then YouTube needs to check, and if you've changed, you're now on your mobile data, maybe it wants to lower the resolution of whatever you're watching before it starts resuming the video. So that's an example of onResume. So that's also a method that we can send data to. It's less useful, but I've included it here just for reference. And then onPause and onDestroy. Similar idea. OnPause is called when you leave the activity. So again, if I'm watching YouTube, then I go to my browser. YouTube's onPause method is going to get invoked before I leave YouTube. And then onDestroy is called when the activity is destroyed. So if you go into your recent apps, and I think on Android you swipe up to remove them from your recents, Android's going to be calling onDestroy for all of those applications or activities. Okay, so enough about that. Let's get into reading some activity code. So the Java archive decompiler breaks the package name into folders and organizes activities accordingly. So earlier we saw that exported activity within Signal's manifest, and the name of it is kind of long, but it was org.thoughtcrime.secureSMS, and the name of the activity is SMS send to activity. So what the Java archive decompiler does is when it decompiles the code, you have the folder sources, which is where it puts all the source code. Then it splits that activity name into values that essentially become folders. So it creates a folder at org, creates a folder at thoughtcrime, creates a folder at secureSMS, and then inside that folder it creates a file SMS send to activity.java, and that contains our decompiled Java source code. So if you're trying to find the decompiled source code for an activity, you just take that name string for it, kind of replace all the instances of the dot with your file separator for whatever system you're on, and that'll help you find where the code exists. So if we go ahead and open up that code file, we can see here the onCreate method is listed up at the top. So that's the code that's called when this activity is started. It calls a couple other methods within there. The important one that I've highlighted in the top rectangle, it calls a method called getIntent. That is a default method that Android provides to an activity if it wants it, and when an activity calls that method, it more or less is getting the data that's been passed as an argument to the Android app. So if I included some extra arguments, some string values or whatever, to this activity when I launched it, getIntent is how the activity would retrieve that data and then do processing on it. And then the getNextIntent method, that's one that has been implemented by Signal. That's not an Android one. Fortunately, it's the next method here in the code. So inside that method, it does some things, and the highlighted line on line 29, it's checking to see if a particular action has a particular value. So that intent variable was passed as the argument, so the intent variable holds all of the data returned from the getIntent call. GetAction is a call to get a particular argument called an action. In Android, these are just arbitrary values that are supposed to kind of help tell an activity what you're trying to do, but it doesn't have to be a particular value. But in this case, Signal is checking to see, is the action equal to, and then it has a long string that ends in send to. And then if it is, it does further processing. So the point here is you can look at the code and you can see where the application is retrieving data that was sent to it, and then you can see where it's actually doing something with that data and starting to compare values. So this is where you can maybe start to manipulate the code flow and try to find an exploitable vulnerability. So go back here. So right underneath that second rectangle, we can see if that action is equal to that value, it goes ahead and calls, it's kind of hard to see, but getDestination for send to as another method within this code file. And if we go and look at that, then it's calling to get additional data from the input data. So the get scheme specific part, we'll see that here in a second. But more or less, again, it's just pulling the data that was sent to it. So if you start to look through the code, you can start to see some of these code paths. So then the next thing to do is, once you think you know how to interact with the activities, you can go ahead and interact with the activity. So ADB has an additional command called AM, which stands for Activity Manager. So it's how you start an activity from the command line. And if you're a vulnerability researcher, using ADB to interact with activities at first is helpful because it's quick, it's easy. You can just do it from your analysis laptop. You could write your own Android application to start this other activity, and if you're reporting a vulnerability, sometimes that is a good idea, but for just analysis purposes, it's easier to use ADB. But just to say that this command that I'm running here could be run from another Android app. It doesn't have to be through the command line like this. So what we're doing is we're telling Activity Manager we want to start this application. We already know that org.thoughtcrime.secure-SMS string stands for Signal. So we want to launch Signal. We want to launch an activity called SMS send to activity, which is the one we were just looking at for the code. The -A option is the action. So recall earlier that we saw that it was checking to see if the action was this send to value. So we're going to go ahead and provide that. And then -ES stands for extra string. So we're sending it an extra string value, essentially a variable, but the string value is, name is SMS_body, and then the value is just test. And the -D option is more or less just specifying a URL. These can be arbitrary protocols, arbitrary content. If you wanted to launch your web browser, then you would put https google.com. But in this case, we're putting SMS2 along with a phone number, and then we're going to start it. And I have skipped over a little bit of the code. If you kept diving through the code, you could figure out that if you send SMS2 with a phone number, it'll do something with it. And this is what it does with it. So the screenshot, I've had to kind of chop it down. My phone's aspect ratio is way longer than that. But what you can see here, go back here. So that SMS2 URL has a phone number, just 208.123.4567. And you look here, Signal read that value, and you can see it plastered all over the screenshot. What's happening here is Signal used to support sending SMS messages, but it looks like that's no longer supported within Signal. So this activity that we found is kind of a dead end. There's no vulnerability here that I've been able to find. But the point is, the input data that we sent to Signal was processed by the app. So Signal took the data that was sent to it externally, and it did something with it. So that's what that exercise is with Signal, is just to kind of show that Android apps can be manipulated to do that. All right, so now let's actually get in and look at a vulnerability that kind of illustrates the dangers of accepting untrusted input without sanitizing it. So this vulnerability that I'm going to walk through is in the Mattermost Android app. I didn't find this, so I want to give credit to HulkVision_ on HackerOne. This person found the vulnerability. If you want to read his or her report, you can see that at the HackerOne link. The Mattermost mobile application is also open source, so you can go look at it on GitHub, and I will actually have some screenshots from the code commit where they fixed it. So the Mattermost Android application exported an activity. This activity expected as input a file path and a file name. The root cause of the issue was the application would read the file content from the path, and then it would write that output using the file name, but it wouldn't sanitize the file name. So if you provided directory traversal sequence in the file name, you could trick the Mattermost application into writing arbitrary file content anywhere within its internal app directory, and you could ultimately get code execution. Excuse me. So if you open up the Android manifest for Mattermost, you can see this activity. So the name of it ends in share activity. You can see it's exported is set to true, so other applications on the device can interact with it. This code, I copied it, sort of copied it out of the report. It's based on the report. Screenshot was not fitting well on the slides, so this is just kind of representative of what you might write in your own Android application excuse me, in order to exploit it. The two parts of interest are highlighted. So in blue, we have the path value. So that's the actual path of the file that the Mattermost app would read. And then in, excuse me, in purple, we have the file name. So the Mattermost app was expecting this value to be something that you would put if you were sending it to somebody else on Mattermost, but the malicious application included a sequence similar to the one listed in the slide there. Mattermost would actually use that value when it saved the file, so it would write this file outside of the expected area. And just really quick on Android, a .so file stands for shared object, if I remember correctly, and it's similar to a DLL file on Windows. It's just shared code. It's a code library. So if I overwrite an existing code library with a malicious one, then my code executes when the app tries to use it. Okay, so this is a snippet of code from the vulnerable activity within Mattermost, and it's assigning file name to the value return cursor.getString. So without going into too much detail, the return cursor object is just the part of the app that's responsible for reading the file or accepting the input data and reading the file. The getString call is Mattermost just requesting the file's name. And as you can see, there's no further processing done. It's just telling Android, hey, give me the string that corresponds to this parameter. If we go back here, parameter's value was name. So it's just asking Android straight up, give me that value, don't do anything special with it. And I've included a link to the commit where they fixed it there at the bottom. So what ended up happening is Mattermost was tricked into overwriting an existing code library file. So the attacker's code would run the next time the application started. So the result was privilege escalation. So a malicious application has gone from being sandboxed in its own environment where it can't read Mattermost's internal files, like your authentication tokens or maybe your messages, to now my attacker code is running within the context of Mattermost's sandbox, and I can read all the data that your Mattermost app has access to. So Mattermost fixed this by creating a new method called sanitize file name. I don't think I have a screenshot of that method, but if you go to the here at the link, you can scroll through the code and you can find that method and see what it's doing. But now they sanitize the value of the file name before they use it further within their app. So this will get rid of any directory traversal sequences. So that's how they fix that issue. So the next thing I want to talk about is another part of the Android framework called providers, or content providers technically. And a content provider is a core component of Android apps that is designed to broker data access. This can either be data access within the application for very large apps like Facebook or Reddit. It can also be data access across applications. So maybe the Dropbox application has some content providers that it uses to manage sharing data if you want to send a file from Dropbox to an email attachment, for example. So a file needs to go from the Dropbox app to your email app. Dropbox uses content providers, or at least they used to manage that. Content provider data can be database backed or it can be file backed. So if it's database backed, then there's usually a SQLite database somewhere within the app's files. The app is storing data in there, and it uses a content provider as kind of a way for other apps to access the data without having to know everything about how that database is structured. File-backed content providers are usually storing files on disk, and then they use the content provider framework to allow other apps to just read the files. It's important to note that content providers don't have to implement either of those. Technically, Android content providers are just implementing certain methods that the Android framework calls when another app tries to access that provider. So you can insert whatever content you want, and I've seen some apps that just return hard-coded strings, things like that. But the purpose of a provider is for data access. And they can be made available to other apps. They can be exported, which as a vulnerability researcher is of interest to us. If you're looking through the Android manifest, you'll find providers with the provider tag. And similar to activities, if they have the Android exported equals true attribute, then that means any application can talk to them. Providers also have a value called Android authorities. This authority string, is how Android knows that someone wants to talk to this particular provider instead of other providers on the device. So many applications implement a lot of providers, so Android needs to know which application it should route a request for content to, and it uses the authority string to figure that out. You access a provider in a similar way that you would access a website, through a URL. And content providers use the content URL scheme. Then instead of a host value like you would for a website, you have the authority value that identifies which provider on the device you want to access. And then you can include an arbitrary path. Whatever you include after the authority string is dependent on the particular provider and how it handles the path. So you can include URI values, you can include query parameters. It's pretty arbitrary after that. These are some of the methods that the Android framework can call within your provider that you need to implement. So query is called when whoever's trying to talk to you wants the query data. Insert is called when they're trying to give you data. Those two methods in particular are sort of representative of database operations. Delete method, similar, is called when data delete is requested. The open file descriptor method is called when the other application is trying to read a file from your provider. So if you have a content provider that is implementing file access, then it needs to implement that method. So we're going to look at an example vulnerable content provider and see how this can be manipulated. Usually content providers, if there's a vulnerability, it's data leakage. So because content providers broker data access, oftentimes they are gatekeepers to sensitive information that an app stores. So if a content provider is exported, if there's a vulnerability, it's probably going to just be the fact that it is exported and you can talk to it. So we're going to look at an example. This one is in the Google Docs for Android application. This is a vulnerability I found a few years ago, so circa 2020, so it's been a few years. The Google Docs for Android app, it had a content provider that it exported, and this content provider stored the last bit of data that you copied while you were using Google Docs. So if you had the Google Docs app open and you're working on a document and you copy some of that text, it would get copied to the Android clipboard, but then Google Docs would also write it into this provider. So then if you went to your web browser and you copied data from Wikipedia, well, the Android clipboard got updated, but the data inside this provider did not. So in theory, if you had Google Docs and you copied data on it, then you could come back 3 years later and still see that exact data, no matter how many times you copied data in other apps or your browser or whatever since then. So I have some original screenshots on my blog. I have the URL there if anyone's interested. I had to emulate the screenshots. So these screenshots that you're going to see in these slides aren't the actual ones, because when I took the original ones for the report, they were way too long. So they don't fit in PowerPoint mode. So 3 years ago, I didn't realize I'd be needing properly formatted screenshots. So apologies about that. You can see the original screenshots if you go to that blog link. If you opened up the Google Docs Android manifest and you found this provider, this is more or less what you would see. So we have the name of it. We can see that it's enabled and it's exported. So the exported value is equal to true, so other applications can talk to it. And under the authorities value, we have a really long string, and that's what we use to talk to this provider in particular. So to read content provider, you have to use the ADB shell command, and in this case, this screenshot that I'm emulating, I was actually inside of a shell on my Android device, so I don't have the ADB shell words prepended to this, but if you were trying to run this on your own device, you would have ADB shell, then the rest of it. So the content command tells Android that we want to talk to a content provider. Then the next word, read, that tells it we just want to read data from it. We don't want to write data. We don't want to try and delete it. We just want to read data. And then we supply the URI option, and we supply the content URI. So we have the authority value that tells Android we want to talk to that particular provider, Google Docs one. And then I found you had to include the string text plain in the path, and this was just something that the content provider was checking for. And then if you ran that, you got text back. So you can tell that when I ran that command, it was doing testing that day. I was in a Star Wars mood. So when you're testing an app for vulnerabilities and you're trying to use it, you just populate it with random gibberish and stuff. So in this case, it was Star Wars Day. So that was text that I copied inside of Google Docs the last time I was using it while I was poking around Docs looking for vulnerabilities. So I thought, oh, that's interesting. So then, in trying to understand the vulnerability better, I found that if you included text HTML in the path value of your content query call, or content read call, then you would get back what you had copied as HTML data. Most of this doesn't really matter. It's not actually data that I was writing. This isn't text that I wrote inside of a document. It's just Google's representation of what I copied if it was HTML. And what was interesting about this is if you embed an image inside of Google Docs, at least at the time I was doing this testing, the image was stored at this googleusercontent.com domain with a giant, long, probably random, but the point was unguessable URL string value. So this way somebody couldn't just go to Google and try to read everybody's images that are embedded inside of everybody's private Google Docs. But this URL didn't require authentication to read what was on it. If you knew the URL, Google considered that to be secure enough, at least at the time. So the point here is if I was editing a document in Docs and I copied an image to my clipboard, I could still get that image later through this content provider by asking for HTML text and then taking that URL to the image and requesting it out of band. So I want to talk a little bit about why this was a problem. So if you're using your Windows device or Mac or whatever, on those systems, if you copy data to the clipboard, other apps and services that are running on your system can access the clipboard at any time. So that's not a problem on those systems. Mobile devices tend to be more isolated between applications, so they're a little more concerned about privacy. They have additional controls that sometimes desktop platforms don't have. So on Android, up through version 9, it worked the same as your Windows system. If you copy data on the clipboard, any app on the device could read that at any time until you changed it and copied something else onto the clipboard. Starting in Android 10, Google changed that. So now, when you copy data to the clipboard, only the application that more or less is currently open and you're using has access to the clipboard. Thank you. So if I have a malicious application running on your device and it's running in the background, up until Android 9, I could just snoop on whatever you were copying to the clipboard. I could just continually check what's on the clipboard every 60 seconds or every minute. and Android would return that data. But with Android 10, Android wouldn't do that. The data on the clipboard is only accessible to whatever app is currently open. So consider the example, if you have Google Docs open and you copy data to it, then you go to your browser. Okay, Google Docs knows what's on the clipboard. Your browser also now knows what's on the clipboard because it's the currently running app. You have your browser open, you find a really cool article that you want to send to your friends, and you copy that to your clipboard, then you go to your text messaging application, you paste it there. Well, your clipboard has changed. So the text messaging application only sees the link you copied from the browser. The data that you copied from inside Google Docs no longer exists as far as Android is concerned. It's replaced that clipboard data with what you copied from your browser. So the problem with this Google content provider was Google was now leaking the content that you copied in Docs. Instead of that data just being private to Docs in your browser, now any app on the device could try to talk to this content provider and get the data that you had copied. So it was not a highly impactful vulnerability, but it was breaking an Android 10 security boundary. So Google patched the issue. So this is me trying to re-exploit it after the patch. The provider's still there, at least it was at the time. That was 3 years ago. I don't know what the Google Docs app looks like now, if they still have it. But after they immediately patched it, you tried to read the content provider's data, it would give you an exception error value. And I don't know if they in the long run removed the provider or not, but at the very least you were no longer able to read the data off the clipboard. So that's an example of a vulnerable content provider. Alright, so now let's go back and look at a little bit of a summary of what we talked to. We talked about obtaining an application's files. So in order to analyze an app for vulnerabilities, you don't always need it, but generally you're going to want the APK file so you can look through the code. You want to decompile it so that you can actually read the code. And then you want to do your analysis to see what components of the app are accessible to other applications on the device, and what you might possibly be able to do to exploit it. We talked a little bit about the activities and providers, different components that an application, can implement, and a couple of vulnerabilities within those. But we're just scratching the surface on what you can look for inside of an Android app. There's all kinds of other components that Android allows apps to implement, such as services, broadcasters, receivers, web views, deep links. If you want to learn more about what those are and even other things to look for, there's a few resources I have in the slides. And then there's a book that I got that got me started into looking for mobile app vulnerabilities called the Mobile Application Hacker's Handbook. This book is outdated, so when I say outdated, this is what I was using about 6 years ago to get started into mobile apps. Mobile platforms change a lot, they change fast. So Android 6 years later looks very different than the Android that's presented in that book. That being said, not everything's changed. There's still some things that are the same, and some of that very basic, how to get set up with ADB, some of the components to look for, that information is still useful. So I wouldn't necessarily pay full price for the book, but if you see it for sale at a used bookstore or whatever, it might be worth picking up. And these resources in general, these ones aren't necessarily the particular ones I used at the time, but everything that I've been talking about today is something that I've learned from somebody else's research that they've put in. So just a thank you to the internet in general and the information that's available there to learn. So that's all I have for today. I think we have a little bit of time left. Just want to open it up for questions. If anybody's got any questions or comments. Gotcha. That's a good question. I do prefer JADX over APK tool, and I think if I'm remembering, I haven't used APK tool in a long time, but one of my thought processes at that time was JADX. If I remember correctly, it produces output in a more predictable form than APK tool does. And so what I'll do, since there's some things that I want to look for in the code, is I want to run grep to recursively search through all of the code. And with JADX, it's a little bit easier to do that because the code is in predictable spots. So. Thank you. Good question. Gotcha. Good question. So the question was if I run into any issues with web views or React Native, and those are frameworks. Well, React Native is a framework for developing an Android application using web technology and programming. So if you want to write your app in JavaScript and HTML, React kind of helps make that possible. It takes your HTML and your JavaScript, and it provides interfaces between that and the actual Android framework, which is expecting Java usually. And then a web view is an Android component that can embed a website within your application, or you can use it to open up web content without having to leave your app. I have not run into vulnerabilities with React. I have found a couple issues with web views before. I think the one I ended up reporting to a bounty program was actually a duplicate, but it was still an issue. It hadn't been patched at the time, so still found it organically, which was cool. You can find vulnerabilities in those, and people do. I'm trying to think of some write-ups I've seen. Usually with those, the issue is within a browser, it displays the URL, so the user knows where they are. So if you open up a browser and you go to google.com, pretty easy to see in the URL that you're at google.com and not an impersonation website. Web views, the application developer has to remember to code that as they're building it. So if they don't do that, and you have some way to open the web view to an arbitrary URL, then the user, from their perspective, they're within a legitimate app, but they might be in an attacker's website. So the attacker can have their own web content, like a login page. So I think the vulnerability that I'm remembering is Facebook actually had a web view embedded in their Android app that didn't show that URL. So if you had somebody click on a very specific link, it would open that web app, it would load your attacker web page. You could have a Facebook login page, for example, but there was no way for the user to know that that was actually an attacker's website and that their password was getting sent somewhere that wasn't Facebook. So thank you, that was a good question. There are vulnerabilities related to those technologies. Gotcha. Yes, so Google both scans for some vulnerabilities and they scan for malware. So if you're trying to upload an application to Google Play and it has malware in it, Google runs it through a sandbox, runs it through some probably machine learning and signature scanning, trying to see is the application doing something potentially malicious. Sometimes that doesn't work, and then Google has to remove apps from the store, but they do that. As far as scanning for vulnerabilities, the one vulnerability that I'm aware of that they do scan for is SSL certificate validation. For a while there in the mobile ecosystem, it was a common problem to have apps that were not validating SSL certificates for their network traffic. And that was a problem because that was somebody at a coffee shop or airport Wi-Fi. If somebody was able to get in between you and your destination, that person could intercept your network traffic and read all of your data. But Google now is doing scanning through some of the Android SSL and network communication frameworks, and they can tell when your app's making a call in an insecure way, such as requesting a website and telling Android to ignore the certificate. So if Google detects that in your application, they'll block your app from being published, and they'll tell you, hey, you've got an issue in your app, we detected this, you need to fix it. So yeah, they are doing some scanning. If they're doing other scanning, I'm not familiar with it off the top, but those are a couple examples. Gotcha. For vulnerabilities, I believe Google does publish some of that information as far as if a vulnerability was found in your app, here's what you need to do to fix it. Regarding malicious applications, I don't, so I haven't looked into that tons, so I can't say with absolute certainty, but I don't believe Google publishes that just because they don't want to tip off malware authors on ways to get around their systems and what they might be looking for. But there's potentially some resources available that might list that. I'm just not aware of them. Yep. Oh, that's a good question. Um, so bug bounties, which is where you would probably be making a profit easiest, those can be difficult. Some of the common applications like Facebook are constantly being looked at by bug bounty researchers. It's kind of hard to predict. Obviously, the application is 100% secure until it's not. So as of now, I'm not aware of any live vulnerabilities you could go find and get profit on. Um, but if you're looking to try and either make some bug bounty side hustle money, or if you're looking to maybe do this more for work, I would recommend taking a look at either open source Android applications and just practicing on those. And if you do find a vulnerability, you might not get paid for it because it's open source, but at the same time, it's a good learning opportunity because you're actually going through the steps of looking at a real app. And then if you report it to them, they can fix it. And it's something you might be able to talk about on a resume, for example, if you're looking for cybersecurity work. And then as far as bug bounties go, if you go to HackerOne or BugCrowd, those are the two big ones. You can look through programs. You can filter by which ones offer their Android apps in scope for their program. And then you can go through and download those Android apps, decompile them, look for vulnerabilities in them. A lot of them have probably already been looked at, but that doesn't mean there aren't already vulnerabilities in them. So, yeah, it's kind of unpredictable if you'll actually find anything or be able to find bounties, but it's worth looking and giving it a try. Thank you. That's a good question. Trying to think of how many valid bugs I've submitted to bounty programs with Android apps. At least 5 off the top that have resulted in a payout. One of them was a payout of like $50, so not necessarily like profit, but very little profit. The Google bug that I just mentioned, they paid a $500 bounty for that one, plus a $1,000 bonus because the app was above their 100 million application install threshold. So if you find a vulnerability in an app that has more than 100 million installs and you report it to the developer, you can also report it directly to Google Play, the Google Play security program, and once the developer fixes it, they will potentially pay you a bonus for finding that, even if the developer doesn't have their own bug bounty program. So that's pretty cool. And then as far as skill development, that's a good question. I have not been I haven't tracked my time over the years, but like I said, I started doing this around 2017 for Android apps. Off and on, it's not been a constant hobby of mine, but it will take some time. You'll want to develop skills, and the way to do that is just to get in there and practice and do it. So I'd recommend finding some open source apps, or just even other apps that aren't open source, and just practice. So go through the process, decompile an app, see what activities you can interact with, and maybe try to send data to it. What can I do to exploit it? HackerOne has a feature they call Hacktivity, where you can read other bug bounty reports that other people have submitted, so you can find reports that are pertain to Android apps, and so you can get an idea of, oh, this is what people are looking for, this is their example vulnerabilities, I might be able to go look for those. So that's one way to learn. So thank you, good question. Thank you.